Okay, my wonderful students, let's begin lecture. We're going to be talking about equations of motion for the most part today. I put together a sequence of slides with very carefully constructed diagrams, and they are related to our main objective as students of Galileo, and that is, as I mentioned on day 2, lecture number 2, the prediction of a future state of any dynamical system. Now, this is a slide from lecture 2 that you may recall, and I had that fancy formula. Now, we talked about this formula here, y subscript f equals y subscript I plus very nice. My TA just went out to get a monster. That's why she's my TA. She's very smart. Anyway, so this equation here, y subscript f equals y subscript I plus VIY times t. VIY, just to recall and reinforce, is the initial y component of the velocity, whatever velocity happens to be. If it's moving upward along in the y or downward, it might have an initial negative value there, like negative 2.3 meters per second. And that's what that term is. Plus 1/2 gt squared. Now, in this formula, as I said before, the g that you want to use is negative 9.8 meters per second squared, because in a formula of this, in a formula, you guys were you were flirting with the 6th row, I could tell. Mischievous look on your face. Anyways, in this one, you're trying to get a coordinate. So it could be negative or positive. That's important for establishing your position precisely. Once you set the x and y axis and the z axis, then you have to deal, at least have the possibility of dealing with a negative number. Okay, and so 9.8 meters per second negative is what we use in that. Now, we're going to put it all together now and put together everything that we know, starting from that diagram from lecture 2. Now, here it is. A baseball trajectory, and we know that it's a parabolic arc. And I've just mapped it out. Now, this is a spatial mapping. In other words, X and Y graph paper. The background here is graph paper. That's good. And what we want to be able to do is nail this thing down completely. We're at mission control for Galileo. Mission control nowadays, they're talking spacecraft. But in his day, he wanted to figure out, just like mission control in Houston, the trajectory of a ballistic object like a cannonball or a baseball. So what we want to do is to be able to get the equations of motion, or the time evolution equations for the position of this baseball as it moves. And there's a couple ways to do that. Now, here's where the careful notes come in. The first way to tackle it is by using the spatial dimensions if you have them. And there they are. The height, in other words, you could put this half of the baseball's trajectory inside a rectangle. And I've done it for you. And try to make your sketch really careful. Now, if you make it look approximately the same proportions as mine, the numbers will make sense. If you want to go later and re-listen to this YouTube and do it on graph paper, yeah, it's possible to do that. Because the spatial dimensions can tell us everything that we need to know to predict the future state. If we know, the height and the breadth, we can work out, a bunch of different implications and use some strategies to figure out the equations of motion. Alternatively, you could use the initial velocity to do the very same thing. And so that would be like this pair of vectors here, vector, V-E-C-T-O-R, I believe I've mentioned it already in the text. It is a quantity represented by an arrow. It's usually a quantity with a direction. Velocity is a vector quantity. Acceleration is a vector quantity because an acceleration has a direction. Anyway, here are the two components of the initial velocity. Now, its initial velocity is about 53 degrees here, right? And so it's got a little bit of Vix, initial x component of the velocity. That's this one down here, going horizontally from left to right. And it's got a little bit of VIY. Now, the ratio is about 3 to 4. In other words, this one is about 3, and this one's about 4. So in other words, make your initial y component of the velocity about a third taller than whatever you used for the horizontal component. All right. Now, the theory is that if we know both of those, we can figure out everything about the motion. So that's pretty good. Now, that's what we want to be able to do. We want to get the equations of motion, and then we'll be able to predict the future state of the baseball, or, if we're working down at Houston, the position, the future state, the future velocity, etc., of the spacecraft to which you're assigned. All right, so it just depends on your target. Now, what we're going to do is work with the spatial dimensions this morning. All right, and you're going to have some homework tonight over the weekend, and it's not ready yet for after class, but it will be 4 or 5 o'clock. So you'll be working with equations of motion like this. Let me pause for questions. We really haven't gotten into the strategy yet, but is that guy in the vent? I wonder what class that is. It is? I should give Darian the assignment of checking it out. Kind of a detective operation. Where's that music appreciation class? All right, no questions. Let's keep going. All right, spatial dimensions. Now, I counted the blocks on the graph paper from lecture 2. I mean, I didn't really do anything fancy with it, but it turns out that it's about 20 blocks high on this graph paper and about 30 blocks wide. Okay. Not bad. Now, for a baseball distance of a baseball, unless you're like a first grader in Little League, this is a baseball is maybe going to be measured in meters, tens of meters. So I said, all right, let's call the first half of this baseball's flight 30 meters across and 20 meters high. In other words, every block is 1 meter. All right? And that's a normal size trajectory for a baseball. It's not going to be a home run, but it's going to be all right. Let's see, 90 meters, that's 60 meters would be the full flight. This is just the first half. So 60 times 3 is 180. So this is going to go out into the outfield somewhere. It might be a line drive, base hit. Probably not a home run. Anyways, if we declare this point down here where the baseball starts, the initial position, let's just call it 0, 0 in meters. All right, just for, convenience. Why not? All right. And then if that's the case, then 30 meters across and 20 meters high is point A up here. Now, I've already mentioned the term apogee in the textbook, And let's just review it. This is point A for apogee. Apogee is the fancy gravitational space program term for the point on a trajectory that is farthest away from the center of the Earth or from the surface of the Earth. Apogee. Now, what does it mean? Apo means away. It's a Greek prefix meaning away. So like an apostle is somebody that's sent away on a specific task. G-E-E, A-P-O-G-E-E, that's from the Greek root word G, or geo, for earth. So apogee means the point away from Earth on an orbit, the furthest point away. Now, this thing, the nearest point is 0, 0 for this trajectory. Now, if you're in a spacecraft, I was looking up, on account of John Glenn and Hidden Figures, which, like a slacker, I still have not seen. I was going to go see it Tuesday night, and I forgot. And then Wednesday night, I couldn't go. Last night, but for sure tonight, and this time, no messing around, I'm going to go see it. And I'm going to pay instead of going for the half-price tickets. Did you guys know the Oviedo Mall on Tuesdays, half price, all day? It's very good. But anyways, I'm going to go tonight, hopefully. Now, John Glenn's, in that movie, John Glenn's trajectory, he didn't have a perfectly circular orbit. It was kind of elliptical. So it had a perigee, which is the nearest point. Para means above, P-E-R-I. So periscope. You're scoping, you're looking above, like a submarine above the surface. So your periscope. Perigee, P-E-R-I-G-E-E, that's the nearest point on a trajectory. So this one has a perigee. You don't really think of it for a parabola, but yeah, theoretically, that's the perigee down there. Apogee is up on top. And the thing about this, if we consider this to be a baseball trajectory, the second half of the trajectory is exactly the same, only flip-flops left to right. Let me repeat that. It is a crucial part of our strategy. The parabola is symmetric, left to right, through the vertical line here that goes to the apogee. So you could, if you have room, you could draw the whole rest of the parabola all the way to the point where the outfielder retrieves the ball. Okay? So the parabola, the ballistic arc of this baseball is symmetric left and right. So the second half of the motion, it looks the same, and the velocities are all the same except they're upside down. All right? The vertical components of the velocity are upside down. They're downward because it's now in the second half of the trajectory, it's heading downwards. It's heading back towards the field. Now, I haven't drawn it in, but if you have room, you can pencil in the second half and make it look exactly as closely as you can to an exact copy, but flipped left to right. All right. Now, the reason that that's important for us is the following. The amount of time that the baseball takes to come all the way back down to Earth from apogee out to the outfield, the drop time is the exact same as the amount of a straight down drop. So go ahead and over to the side somewhere, draw a 20-meter drop. Okay? And the key to this is that the drop time from the top of the trajectory back to the outfield is the same as if it was just a straight down drop. Or you could say that the rise time is exactly the same as the drop time. So the amount of time it takes to get up, to rise all the way up to the apogee, go ahead and make a note of this. The rise time from initial point to apogee is exactly the same as the drop time from apogee all the way back down to the outfield, where the outfielder retrieves the ball. Okay, and that's because of the symmetry of the trajectory. All right, so we have left-right symmetry, and we have speed symmetry, left and right, except that the speeds on the left side are upward, the vertical components are upward, and on the right side they're downward. All right, now we're going to use this 20 meters. Now I'm going to drop the baseball. Now watch. This is animated here. Here it comes. Ching! All right, sweet. Okay. We're going to make use of that. That drop time, we know the drop distance. So the drop time, this is the key that unlocks everything. If we can get that time, then we know the rise time. If we know the rise time, we can put it all together. All right? So make a note. Taking advantage of the symmetry and the fact that gravity is only vertical and not horizontal will allow us to get everything. It's kind of like when you're doing a crossword puzzle, and 17 down, can't get it. 18 down, can't get it. 19 down, you can't get it. But suddenly you get 17 across, and now you have a clue. And then you get 21 across, and you start putting, and eventually you get the whole crossword puzzle figured out. So we're going to kind of work through that way. And this is the key. This is the key word that unlocks the whole rest of the crossword puzzle. All right? And that's because the drop distance tells me the drop time. And that allows us to use our strategy. Now, there's the drop distance formula. D equals 1/2 gt squared. Now, according to our graph paper, that's 20 meters. All right? Now, we know what G is. It's 9.8 negatory. Actually, in this one, we're going to use positive 9.8 because it's just a drop distance. Okay? We're not trying to get a coordinate yet. All right? So we can just use positive 9.8. And the strategy is, whatever that drop time is, from 20 meters high back down to the outfield, that's the same as the rise time. So the time that it takes to go from the initial point, 0, 0, all the way up to apogee, that is my rise time, and that's the same as the drop time. And now that I know how far it drops, I can nab the drop time. All right, so let's put it together. First things, put in what you know. Okay, 1/2 G, that's this, 4.9 meters per second squared. We're plugging in some numbers. Now, we don't know what T squared is yet. That's what we're trying to figure out. But we do know the drop distance, 20.0 meters. All right? So that's good. All right? And so now, if I want to get T squared by itself, algebra-wise, T squared by itself, what's your next move? Divide both sides by 4.9 meters per second squared. There it is. Okay. And so T squared is going to be 20.0 meters in the numerator and 4.9 meters per second squared in the denominator. And hey, you guys, the meters cancel, and the per second squared, remember, division by a fraction is the same as multiplication by the reciprocal. So the per second squared in the denominator goes into second squared in the numerator, right? And the meters are canceled. And so now you calculate, and the unit s squared, second squared, that's good because I'm supposed to have the square of a time, T squared. It should be, it's not going to come out kilograms or something unless you make a mistake. It's not going to come out in square meters. That would be a mistake. Second squared for T squared, good. We're looking good here. All right, so you work that out. It's about 5, or excuse me, it's 20 divided by 4.9, so that's about 4, you know, if you're just doing it in your coconut. And if you do it on a calculator and keep a bunch of digits, 4.0816 seconds squared. Now that's t squared. That's not t itself. Okay? So Anastasia, if we're going to do t itself, we want to square root that. All right? So that's what we're doing here. All right? So now you put in 4.0816 in your calculator and then hit your square root key. And on an iPhone, it's got a square root sign with a little 2. That means square root. But if you have a regular calculator, and as I mentioned last time, start bringing your calculator to class because you're going to need it, and you won't be able to use your iPhone or your cell phone in exam 2, which is coming 2 Tuesdays, a week from Tuesday. All right, February 7th. So you do the square root, and you work that out. Who's got an answer for me? 2 point, yeah. So it's a square root of a number pretty close to 4. So the square root of 4 is 2. So my answer better be close to 2. And yeah, rise time 2.02 seconds to the nearest hundredth of a second. That's good enough for government work. All right. All right. You verify me over there? You verify? I saw. Yeah, I saw you holding up your calculator. Yeah, good. Okay, good. So always check me, and because sometimes, you know, I might try to, you know, throw you for a loop, and I don't want you to get caught napping. By the same token, sometimes I have a typo, and I've been caught napping by a typo. You want to catch me on that. All right. Now, just to reinforce, here's the cancellations. Here and here, okay? And the second squares go up to the top in the numerator, and then the square root of s squared is just s, so this is 2.02 seconds. All right, questions about this? Yes, Anastasia. On this one, we're doing a distance, we're doing the drop distance formula, so 9.8 is fine. But when we get to the equations of motion, then you got to use negative 9.8. Now, if you're on, as I mentioned before, if you're on another planet, you know, like Mars has got a, I looked it up, it's 3.4, I think, meters per second squared on Mars. The moon is like 1.6, something like that. But, you know, we're mostly going to be, and if I use the symbol G, it's always going to be 9.8. And if it's in an equation, you're going to use negative 9.8 frequently. Now, rise time tells me how much upward speed I've lost. You know, because every second of motion upward, I'm losing 9.8 meters per second of speed. You know, so in 2.02 seconds, I've lost about 9.8 times 2. That's 19.6. All right, so that tells me how much I've lost. All right, so our strategy is to use the delta V formula for this acceleration. And in this one, Anastasia, yes, we're going to use negative 9.8. Here's what we're going to use. What we know is negative 9.8 meters per second squared. And the reason this is important, Anastasia, is because we're going to be doing the velocity components. And with velocity components, you definitely want to have a negative if it's downward and a positive if it's upward. So you got to, you know, and this is where you put it in. If you handle this correctly, you'll get the right plus or minus to indicate up or down. All right. So here's what we know. Negative 9.8 meters per second squared. See, I'm going to learn all your guys' names. So, like, now, with the LA Dodgers hat right next to it, what's your first name? Ashley? Ashley? Okay, good. Ashley. See, because I can, every time I call on Anastasia, you're going like this or something. But see, I can call on anybody Ashley. See, I know a bunch of names in here. That's good. All right. Cancellation. 1 power of seconds in the denominator of G, all right, it's per second squared, cancels with seconds up here in delta T. All right. Now, what that leaves me, units-wise, is meters per second. And that's what we want for a speed. All right. So that works out nice. Now, if you calculate it out, and I've used a few more digits than just 2.02. I think it's 2.0203, blah, blah, blah. Anyways, 19.799 meters per second negatory. All right, now that's my delta V. That tells me that number is negative. That means that I've lost upward speed. Or if I were going downward, it would tell me that I've gained downward speed. But this one's initial upward motion, so that tells me how much I've lost. And that tells me the entire amount of velocity that I've lost. All right? And the reason is up at apogee, I've lost all my upward speed. Now, we're going to make use of that here in just a second. Because delta V, that's the same as V final minus V initial, or in this case, V subscript AY. The y component of the velocity at apogee minus initial y component of the velocity. Okay, that's VIY. And that's equal to negative 19.799 meters per second. And I'm keeping, I'm not finished with my calculation, so I'm keeping a few extra digits, more than I normally do. And then we're going to round off towards the end, but not yet. Now, this quantity over here, that's the endpoint quantity for point A. So normally I use the letter F there for final, but here we've got a letter to denote that point. But over here, VIY, that's the initial y component of the velocity. All right, now I don't know what that is, but we could figure it out directly because we do know that VAY here is 0. Because at point A, you've stopped moving upward. You're at apogee. You've lost all your upward. And you're about to start acquiring downward velocity on the second half of the trajectory. All right? So that's all right. And my unknown here, the initial component, the initial y component of the velocity, if you think about it, that's the only unknown that I have. So I've got numbers everywhere else. So I can get it. It's good. We can get it. All right. Matter of fact, this whole business here of 0.00 at apogee, you can even cross that out. Just go ahead and cross that out, or, whatever you want to do. Erase it. I'm going to erase it. So really, this is all I've got. Minus VIY equals minus 19.799 meters per second squared. So that means that VIY itself is positive 19.799 meters per second. And my wonderful students, put a big check mark. Ching! We've got what we need for our fancy y subscript f formula. All right? At least we've got the main part of it. But here's the other question we haven't tackled yet. What's the initial horizontal speed? This is vertical initial speed. What's the horizontal component? We can handle that. And the reason that we can handle that is because, well, let me pause for questions. Yes. Yeah. In the delta equation, deltas are always a difference. Greek letter delta, D for difference. D for delta, D for difference. So it's always a subtraction. And it's always later minus earlier. All right? So V subscript F minus V subscript I. Okay? So what is your name again? Jody. Jody Meister. If you're trying to figure out VIY and you're using the delta V, you're going to have a leftover minus sign in front of the VIY, which is what we got over here. But now if we were in some other problem, we were trying to find VFY, then that would have a positive sign in front of it because of the definition of delta. All right, the deltas are always final minus initial, later minus earlier, 2 minus 1, V2 minus V1, whatever, whichever one comes later, subtract from the one that comes earlier. All right. So the minus sign is in there because of that. We handle it because we want VIY itself. We don't want, minus VIY is nice, but, because the speedometer, your speedometer, for instance, doesn't tell you your negative, the negative of your speed. It just gives you a positive number. Okay, that's what we want, whatever the speed is. All right. Now, horizontal speed. How do we get it? Well, we use this fact. There's no such thing as horizontal gravity. All right. And Dare, this is okay. We're going to use that fact because it means that the velocity, the x component of velocity, as a function of time, Vx of t, is a constant. We have a constant horizontal speed. Gravity is vertical, so it doesn't affect, if you have any horizontal component of velocity, that's unchanged. All right? So that's going to be, so many meters per second. So that's going to be ditto marks all the way through the trajectory, your horizontal component. And we talked about that at the end of the lecture. Now, the 30 meters of horizontal motion for, my spatial measurements is basically 30 meters. That's a distance rectangle. So I can use the distance rectangle formula. There it is, delta x, Vix times delta t. Now, we first used the distance triangle formula, or excuse me, the distance rectangle formula. We didn't have subscripts on it, but these are the subscripts that are appropriate. This is the velocity in the x direction for the entire time of travel, 2.02 seconds. Matter of fact, let's just plug in some of the numbers now. Okay, delta t, 2.02 seconds. And hey, we know what XA, Jody, delta x, x final minus x initial, x of apogee minus x of initial. Good. But we know what both of those numbers are. One's 30 and one's 0. So, ching. So we're looking good. We're plugging in the stuff that we know. And as I told you, the spatial dimensions give you everything. If you have both the width and the height. Now we're using the width. But we've already used the height. It's kind of built into the 2.02 rise time. 2.02 seconds. All right, so again, just kind of mentally cancel out that 0. 30.0 meters minus 0 is 30.0 meters. All right. And so you want to get Vix by itself. So you divide both sides by 2.02 seconds. And that's about 15, maybe a little bit less. All right. Now double check on your calculator. Do not let me catch you napping. It's going to be a little bit The denominator is a little bit bigger than 2, so the quotient is going to be a little bit smaller than 15. So 14 point. Okay, good. I get 14.849, and I'm carrying a few extra digits for safety because I'm not done yet. But we're almost done because now I can put everything together. Now that's all we've been working towards. We just want something to bring it all together. Just like, you're in the major leagues, you're making a pennant, you're trying to get the pennant. Sometimes you just need something to bring it all together. And that's what we're doing. All right? So we've got VIX, we've got VIY, we've got initial position, initial X, initial Y. So we're good. We got everything we need now. All right, so here's what we got. All right. Vx as a function of time. So any time, 14.85. Ching! And that's because there's no such thing as horizontal gravity. The x component is a constant. All right, now gravity is where things start changing. Gravity is vertical, so the only thing that changes with time is the y component of the velocity. So Vy of t is whatever I started with, and now I'm writing it as, instead of 19.799, I'm going to write it as 19.80. Okay, I've rounded off a little bit. Meters per second. So that's my initial speed. And then the change is here. This is gt, if you will. All right, so this is VIY plus gt, and it is negative 9.8 meters per second squared times t. Ching! So now you can predict the velocity at any point you want, like this one up here. And for homework 4, you're going to be dealing with that. Matter of fact, I might even give you this problem and just tell you to work it. See what you can come up with. All right? 20 by 30. All right, now questions about this? All right, now these are the equations of motion for velocity. All right? I've got the x and the y components squared away. Now we're ignoring the z component. That would be, in this graph paper, it would be up out of the paper or down into the desk. So we're going to ignore the z component. But if you're really playing in baseball on a field and it's a windy day, sometimes a really high ball, a really high fly ball, it can curve a little bit. So in other words, it's not a straight XY motion from home plate. It might have a little bit of up, a little bit of outfield, and a little bit of left or right, depending on the direction of the wind. So a crosswind will blow it. But we're going to ignore that here. So those are my equations of motion for the velocity. Now, what are the equations of motion for the position? X of t and y of t. Here they are. All right. Now, the first one, x subscript f, or you could write x of t if you want. X of t. Initial position, 0.00. You don't really even have to write that in, but I wrote it in so things would look kind of organized. Plus 14.85 meters per second times time. So that's just a distance rectangle. But down here in the y component of the position, or the y coordinate, so y subscript f, or if you like, y of t, This is where the time dependence comes in. And it's actually got a t and a t squared. Now, the initial position is 0.0 meters by design, okay, home plate. And the first term, here's a distance rectangle, all right, 19.8 meters per second times t. That's the initial y component of the speed, VIY, which that was the first thing we figured out. Actually, the first thing we figured out was the drop time, but that's not encoded in, well, it's encoded in all this, but no specific drop times in here. And then here's 1/2 gt squared, and I just converted it to minus 4.9 meters per second squared. Yeah, that's 1/2 g. And in this one, as I've mentioned before, Ashley, you want to have a minus sign to indicate, you know, you've got some downwardness possibly. And by the way, students, this particular equation or set of equations, it'll map out the entire arc of the parabola until you get all the way back down to the outfield, y f equals 0 again. All right? And you can figure out when that is. It's not too hard. Fairly easy to do. But yeah, we've got all this stuff squared away. We're looking really good. So if you take any point like this one up here, I can ask you, okay, at time t equals 1.4 seconds, you know, what's the velocity? What's the y component? What's the x component? What is its x coordinate? What is its y coordinate? And with these equations and then the velocity equations, you'll be able to figure that out. Matter of fact, you'll be doing that in homework 4, all right, out the wazoo. Question? Whoa, good eyes. Dr. B, yeah, that's supposed to be t squared. Ooh, I'm going to have to change that. You know, you guys are the, unfortunately, you're the ones that always catch the typos, as you've just done. Second, the noon lecture is the one that I always try to correct my typos for the noon section. Anyways, yeah, that's supposed to be t squared there. Question?
In the negative 4.9, you stated the negative indicates what?
Downward direction of the acceleration due to gravity at the surface of the Earth. In other words, gravity is downward. It's a downward pull everywhere toward the center of the Earth. Okay? So, and there's nothing horizontal. So there's another way to look at it. Up here in the x subscript f, there's no t squared version, t squared part of the equation up there because there's no acceleration. You only get t squared if there's some kind of an acceleration, some kind of a distance triangle, right? And sorry for screwing this up. I'll try to change it if I can for the podcast, for the YouTube. All right. Now, my final comments are that we've got equations of motion for this thing completely nailed down. All right. And we can do as much predicting as we want to. Matter of fact, there's nothing in here about the mass of the baseball. And you know, Galileo's famous experiment, the cannonball and the musket ball dropped at the same time from the Leaning Tower of Pisa, and they get to the ground at the same time. That's why. There's no mass term in this. Now, in some other system that's not free fall, you might have to take into account the mass. And to do that, you have to use Newton's laws of motion. So let's keep going. I want to do some clicker questions with you to get your mind rolling. So get your clicker up and turn it on. And if you, did you synchronize?
Yes.
Okay. And if you're using your clicker for the first time, hold the power button down and then select, when the rectangle in the upper left of the screen flashes, type in B for Bravo, Bravo. Okay, and then you'll get the Go Nitro message and then the Ready message. Here we go. A blue car. Read carefully. Notice option F. All of the above includes none of the above. So, but the students can't select option F for this anyway, so it's not a danger. Okay, the blue car moves to the right at constant speed. Okay, 20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, the correct answer is B. Most of you got that. Very good. Yeah, option A is no good because acceleration and constant speed do not mix. So, all right. So here's a little blurb. So if I say that the car is moving at constant speed, it means that you could write some statement like this. Right? This would be a mathematical statement that is consistent with this blue car moves to the right at constant speed. By the way, in this notation here, the V subscript I with a little tiny arrow over the top, that little tiny arrow means it's a vector, okay, and not a speed. It's a velocity and not a speed, okay, and that's why I also have to write down the word comma rightward in this example. All right, now we're going to have some more clicker questions, but first we want to get to Newton's second law. We talked about the first law before. Now, Newton's second law is what happens if you have unbalanced forces. You know, so if LeBron James is pulling to the left and Dwight Howard is pulling to the right and one of them is stronger, you know, one of them is going to win. How do you handle that? Well, that's what Sir Isaac Newton figured out how to do. You know, his idea was that to change the state of motion of an object, you have to either push it or pull it, right? So to accelerate it, you know, even to change its direction, you've got to have some kind of a pull or a push force. So if you add up all the forces, and if something doesn't balance, then you have a net force, all right? And the notation for that is a capital F with a subscript NET, net, all right? So in this example that I've got diagrammed out here, Dwight Howard versus LeBron James. So let's say that Dwight Howard has a positive rightward force of 100 metric units of force. And LeBron James, weenie that he is only able to pull with 80 metric units of force. So this one's leftward, as the diagram shows, and therefore in the equation here, I put a minus sign, minus 80, to signify leftward. All right. Now, the nice thing is that if you have your plus or minus signs racked up here and here properly, then all you got to do to get the net force is add them up carefully. So 80 plus a negative, 100 positive plus a negative 80 is a net of plus 20. So rightward net force. So the net force is toward Dwight, and he wins the battle. He gets the ball. Right? Now, another thing that Sir Isaac Newton said was, if you have more push, in other words, a bigger net force, you'll get more acceleration. And he said, if you have more mass, though, you'll have less acceleration. All right? Now, if the simplest way of putting that into an equation is to say the acceleration, if it's a quotient, the net force will be in the numerator, because the bigger the numerator, the bigger the quotient. And the mass of the object would have to be in the denominator, because more mass, smaller quotient. And that's how his third law works. A equals F net divided by M. Right? And here's another way to look at it. F net equals MA. And my wonderful students, this particular here is, bigger version of it. F equals MA is something that the engineering majors, long may they reign, have got permanently engraved in their brain. As a matter of fact, almost any science student is going to constantly be thinking about F equals MA. They're equivalent. A equals F over M. F equals MA. They're equivalent. All right? And, as we've been talking about hidden figures and stuff, the acceleration, the slope, I'm going to say this slowly so you can make a note of it. In the distance trapezoid, the slope of the triangular part is the acceleration. The acceleration is the ratio of the net force on the object. So now in terms of NASA, you're talking the effect of the rocket motor and a little bit of air, well, quite a bit of air resistance. And then you're also talking about the mass of the rocket, right? And both of those things are changing through the initial few minutes of launch. And that is why the slope of the distance trapezoids are changing all the time. And that is where it becomes very difficult. They have to test the rocket engines so they can know the force. And they have to know how many kilograms of rocket fuel go blazing out the tailpipe per second, or per millisecond. And then they can do their F equals MA calculations, but it's not easy. All right, let's talk about some details. Now, we know that the definition over here, upper right, of acceleration, delta V over delta T, and Sir Isaac Newton's concept, A equals F net over M, or F equals MA, that actually allows us to use this formula here, F equals M times delta V over delta T. All right? And if you think about it in terms of measurements, you need time, distance, and mass measurements. You need time and distance to get delta V. Delta T is a time measurement, lapse time. And the mass M in kilograms is basically something that you get from a balance, at least initially. That's how all that worked. The calculations are velocities and acceleration. M is a measurement. The mass, you don't really, I guess you could calculate M based on other stuff, but usually you just read the mass off your measurement device. But delta V is derived, so delta T is stopwatch time. All right. Now, the reason I'm bringing this up is that if you come to a stop, so you're doing plyometrics at the gym, you're doing a plyometric, and plyometric, one plyometric workout, famous one is box jumping. You jump up onto the box, you jump down off the box, develop your explosiveness. It's a good workout, okay? But the amount of stopping time, when you jump up on the box, you're going to bend your knees a little bit. And when you jump down from the box, you're going to bend your knees a little bit. In other words, that adds to your stopping time. So the more stopping time, now that's going to be in the denominator. Now the amount of delta V is controlled by how high the box is, or actually how high the box is, and then how you might jump a little bit upward from the box. So your highest height controls delta V. All right, but delta T, stopping that, how long does it take to stop that? That's controlled by, like flexing your knees and stuff. Okay, so more stopping time, bigger denominator, smaller force. By the same token, less stopping time, smaller denominator, larger force. Another way to look at this is in a car. If you're, God forbid, in a car accident, if you're going 60, no, I'm not going to. If you're going 10 miles an hour and you plow into a brick wall, you're going to stop in about 1/10 of a second. Very small stopping time. But if you're going 10 miles an hour and you plow into a snowdrift, in a snowdrift, a big pile of snow is going to stop you really gently. It's not going to wreck your car or anything. I mean, the brick wall is going to, even at 10 miles an hour, it's going to pretty much, wreck your car pretty badly. Okay, but a snowdrift, nah, not really. Because the delta T is so much smaller, so the stopping force, for the snowdrift, delta T is much bigger. It might take you a full second. Okay, so the stopping force is much less. And therefore, it's easier on your car. So in terms of box jumping, longer stopping time, less stopping force. And did I say that we're going to have some questions in homework 4? Yeah. We're going to have a bundle of questions in homework 4. All right. So that's, and you guys, I have some bad news. I guess some bad news. It may feel like that. The midterms are supposed to be midterms, right? The final is supposed to be cumulative. The midterms are not supposed to be cumulative, but effectively they are, because we're never going to stop talking about F equals ma, for instance. We're going to be continually using G. We're going to talk about free fall a lot. So you're learning that now, but we're still going to be talking about it on midterm 3 and then the final. So it's, so Newton's second law. Let's do another quicker question. Your liter bottle has a mass of 1.00 kilograms, which is pretty good. If it's a liter of water, that's 1,000 cubic centimeters. That's about a kilogram, 1,000 grams. And you put a pull force on it of 1 meter per second squared. Or excuse me, your acceleration is 1 meter per second squared. What's the size of your pull force? "15 seconds. And you better write this one down as because this is actually going to give us a definition. 10, 9, 8, 7, 6. Come on. 5, 4, 3, 2, 1. Zero. Okay, 83 people answered. Yeah, this one, A is the correct option. Make a note of that. 1.0, it's a mass times an acceleration. So now we've got a mixture of units, kilogram meter per second squared. And that, my wonderful students, is the official unit of force in the metric system. It's called a Newton. 1 Newton accelerates 1 kilogram objects at an acceleration of 1 meter per second squared. All right? So that is the functional definition of the Newton. And the abbreviation for it is capital N. And some books capitalize the word Newton, and some of them don't capitalize. I usually capitalize it. And the symbol is always capital N. But make a note to yourself, it's always good to be ready to change. If you're working on an equation, if you have an equation that has newtons in it, sometimes you want to convert the newtons and erase Newton, capital N, and write in kilogram meters per second squared, because you might want to do some cancellation of seconds or meters or something like that. So just keep that in mind. Now, let me ask you a question. What's the acceleration due to gravity on the surface of the Earth? 9.8 meters per second squared. Okay. What's the gravitational pull force on a 342 kilogram T-Rex? Let's do that. Numeric question number 3. And hey, you guys, the way to get a number in is to use the up and down arrow. In fact, hit your refresh key. If you don't have a letter, actually, do you have a clicker? Okay. Okay, now what do we start with here? Go Nitro, ready. Okay, when you get a numeric question, hit the refresh, and you'll start it with the number 1. And then to get other numbers, you just go down or up, And then when you got the right number, then you go to the right, and you start typing in another number, and you got to go. So it's kind of like those old stinky cell phones, where you have to type the letter 3 times to get the letter F. But this one you got to. But it's got a bunch of different letters. It's got ABCs and symbols and things. So, okay, I'm using Darian's clicker here. I thought you didn't have one.
Yeah, I do.
You do? You just keep it. Yeah, good. Okay, I'm typing in 1. And then when you're done, hit the send key as before. All right. And try to do it carefully. Ooh. And give it to the nearest Newton. So don't give me any decimal points. I see some of you with the right answer, but round that off to the nearest Newton. There we go. Oh, some of you rounded to the. You didn't round right. There we go. Okay. All right. I can see you guys progressing here. It's the clash of the ages here. The corrects and the there's still some. 3 of you have an incorrectly rounded correct number. Who typed in 1? That was me, actually.
That was you, yeah.
Yeah, but somebody else did. See, 2 people typed in the number 1. Okay, 1 is not the right answer. And we're just doing practice questions today, but on the exam, you're going to have to use your clicker to type in a good answer for different calculations. Okay, 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, switch to computer, please, for a second. All right, now a bunch of you guys, the correct answer is 3352. And a bunch of you typed in 3351.6, which is okay, but you didn't round off right. Okay, so remember, if I ask you to round off to the nearest Newton, just give me a whole number, the nearest one. And can you see if you can draw down and look at some of the other answers? 34.9. I don't know how you get that. 1676. I'm not sure how you get those. Anyways, go ahead back to laptop, please. All right. Correct answer is 3352, and it's just mg. 342 kilograms times 9.8 meters per second squared. And to the nearest Newton, that's 3352. All right. So the weight force is always mg for whatever the object is. Question?
How come for this one you did divide by 2? Because that's how I got 1676.
Because it's a force, so we're calculating ma, or in this case mg. And so there's no 1/2. You're thinking about the distance formula, and that's 1/2 at squared or 1/2 gt squared? No. This is a force calculation, so we use F equals ma, or in this case, F equals mg. Okay? So as I said, 342 kilograms, m, times g, 9.8 meters per second squared, and to the nearest Newton, it's 3352. Okay? All right. A few more details about mass that we're going to need. We're now at the point where we have to start dealing with mass. The more mass, the harder it is to change your dynamical state. All right, so just think of it. You know, if you have a cart of groceries at Costco, and you know, sometimes I'm waiting at the snack bar for my wife to finish shopping. I always bring a book to read while she's shopping, and it's fun to watch the people coming and going, or people going. And some of the stuff, they are loaded down with stuff at Costco. But if you have an empty cart, it's easy to move, you know, get it going. But sometimes those carts are just loaded down, and it takes a lot of oomph to get it going. So the more mass, the harder it is to change the dynamical state. The kilogram is defined in terms of water. So a cubic centimeter of liquid H2O is equal to, the mass of it is equal to 1 gram. So in a balance, if you put a single cubic centimeter of water, it will balance an object on the other side that's exactly 1 gram. All right? So you put your object in the balance, and then you count the number of cc's of water that you have to put in on the other side. So for instance, this basketball is trying to balance with a kilogram of water, and the basketball is not even close to a kilogram. I mean, that would be pretty hard. That's more like a medicine ball, actually. Okay, so basketball is not that big, so it doesn't balance. So you add water to the left side of this balance, and you count up how much water you have, and then that's the number of grams that you've got. And you convert that to kilograms. So that's your basic strategy. And that's how we've defined the gram. Now, that being the case, we now have balances where they have, you don't use water, you know, you have pieces of metal that they've balanced in a balance with water somewhere along the line, and now they use that and stuff. So, but yeah, in the metric system, that's how it started anyways. Liquid water. It's kind of cool. All right. Now, let's continue to keep moving here and talk a little bit more about Newton's second law and directionality. Now, the whole idea of directionality is simply this. Force is a vector. It has a spatial direction. You know, gravity, spatial direction is straight downward. But some other force might be a little bit of downward and a little bit of leftward. All right? Or a combination of X, Y, and Z directions. All right? So you got to be able to handle that. So the The net force is equal to the mass times its acceleration, and it points in the same direction as the acceleration. All right, so if you get a force 45 degrees from your velocity, so if you're in this Ferrari and you're moving forward, and you get this little alpha particle here blazing into your car from aft and port, that means you're going to get a little bit of a bump, and it's going to increase your speed forward, and it's going to change your direction, all right? Because the net force is 45 degrees away from your velocity, all right? So that's encoded in this statement. So this is another statement where we have a vector symbol for the net force, a little arrow over the top of the capital F. And there's a vector on the other side for the acceleration. Now, mass is simply a number. It doesn't have a direction. Nobody says, well, the object has a mass of 2.5 kilograms to the north. No, you just count up the number of kilograms, all right? The number of cc's of water, all right? So whatever direction your acceleration is, that's the direction of the net force. Now, you can't measure a force directly. What you do is you figure out the direction of the force by measuring the motion of your object. So basically, if you can figure out the direction of the acceleration, and by the way, students, make a side note here, the direction of the acceleration is also the direction of delta V. So if you know the direction of delta V, because that's the numerator of the acceleration definition. Okay? So if you know the direction of delta V, that's automatically the direction of the acceleration. And that's automatically the direction of the net force. Now that's not the direction of all the forces, but the net force, yeah, that's the direction of it. Okay. Is there a pair of skateboards in the hall? And I've already asked this question. And the answer is yes, but we're out of time. Bring your skateboards to class on Tuesday. Be ready for homework 4 tonight. And I'll see you next week. You're dismissed. That's good. Where's my cursor?